Hello friends, welcome to another tutorial in digital system design. In this tutorial we'll talk about methods of fault location and detection in combinational circuits, and we'll discuss the fault table method. Let's understand this with a question. For a combinational circuit like this, where we have the output Z equivalent to x1 bar and x2, and then further it is ORed with x3. Now this combinational circuit has three inputs, x1, x2 and x3, and it can have possibly 8 different combinations of output for 8 different inputs. So for all those combinations of inputs that we must inspect to check whether this circuit is fault free is what our objective is. It will become more clearer as we go on and solve this question. So let's go step by step. So if you get a question like this, you'll be asked to find the input combinations for which you must check this circuit for faults, using of course the fault table method. Now the first step is to name the terminals A, B, C and D. So for that I'll name this as A, B, and this terminal is C and this terminal is D. And we know that the output is x1 bar, x2 plus x3. So we make the table and compute the output first without any fault, and then we'll compute the output when A is stuck at 0. That means that this terminal is always 0. No matter we are changing the input here, it is always stuck at 0. And similarly we'll check the output when B is stuck at 0, C is stuck at 0, D is stuck at 0. And in the final step we'll make all these terminals stuck at 1. So we need to compute the output for a lot of cases. Firstly, we'll need to compute the output for no fault. So we'll need to compute it 8 times, then we need to compute it 8 times when A is stuck at 0, 8 times when B is stuck at 0, and so on and so forth. That might sound a lot, but I'll show you a way in which this can be done very quickly. For x1, x2, x3 inputs, I've written down all the possible combinations, and I've mentioned x1 bar explicitly here because the input x1 bar goes to this AND gate. Now in order to compute the output Z without the fault, we can see when for 0, 0, 0 it will be 1 and 0 plus 0, because for 0, 0, 0 x1 bar becomes 1, x2 is 0, x3 is 0, so it will give me 0. So my output without fault will be a 0 here. Alright, and then for 0, 0, 1 we see that this is still 1 into 0 plus 1. So it is 0 plus 1, which is 1. This will be 1. So this is the list of fault-free output Z. And you could populate this table like this. You could pause the video and write down these outputs. Now when A is stuck at 0, so let's inspect that case. This is 0. Now when this is stuck at 0, this terminal is stuck at 0, of course we'll get a 0 here. And because if we get a 0 here, everything will depend upon this. And this is, by the way, D. This was our B. This was our C. Now when C is 0, one input of OR gate is 0. So everything will depend upon the other input. If this input is 0, we'll get a 0 here. If this input is 1, we'll get a 1 here. So that means if A is stuck at 0, my output will be D, and D is nothing but x3. So A naught will replicate D, which is nothing but x3. So I can simply write 0, 1, 0. So the output will always be x3. So you could write that down. And same is the case with B stuck at 0. If B is stuck at 0, the output of this AND gate will always be 0 and D will be forwarded to the output. So this will also follow x3. So that is how you can quickly do it. Now let's look at the case when C is stuck at 0. When C is stuck at 0, of course D is again going to be followed. So I've written down x3 as it is. When D is stuck at 0, then what will happen? It will follow C, and C is nothing but A and B. So it is going to be 1, 0 will be 0, 1 and 0 will be 0. So wherever we see a 1, 1, it will get a 1, otherwise we'll get a 0. So these are the cases when the terminals are stuck at 0. Similarly, we can see when the terminals are stuck at 1. When the terminals are stuck at 1, let's see when A is stuck at 1, everything will depend upon B. So whatever the value of x2 is, it will be replicated at C. So in other words, we have B, which is x2, and x3, right? Because A is not deterministic, A is 1, so the value of B will come here and D. So B or D will be the output. So just OR these two. So you get, when these two are 0, only then we'll get a 0 here. Otherwise, even if one of them is 1, we get a 1. Now let's look at the other three cases. I hope you'll be able to follow the suit. When B is 1, A will come here, and A plus D will be Z. Now A is nothing but x1 bar, so whenever 1 and 0 is there, so we get a 1 here, and so on. When C is stuck at 0, when C is stuck at 1, then we always get a 1. When D is stuck at 1, we always get a 1. So these two columns are always 1. So it is very important to populate this table. The first column is to calculate the output without faults. The next two columns are calculating the output when one of the terminals is stuck at 0 and when one of the terminals is stuck at 1. Now the next step is to see that for input 0, 0, 0, our output should be 0. Our fault-free output should be 0. And A being stuck at 0, B being stuck at 0, C being stuck at 0, D being stuck at 0, A being stuck at 1 will not cause deviation at the output. The output is still 0. So what needs to be checked is B stuck at 1, C stuck at 1 and D stuck at 1. Please understand, if the fault-free output is 1 and the terminals which are stuck at either 0 or 1 give the same output, then we do not check them for faults. So similarly, in the second case, only D stuck at 0 could be the culprit for the input 0, 0, 1. So this is the rationale behind populating the second table, which will look something like this. Please see, our fault-free output for 0, 0, 0 was 0. So what we do is we put a cross at these three conditions. Then we put a cross here because all the others are replicating the same fault-free output. And now the output needs to be 1 and these three are causing an output 0. So we put a cross here, these are not causing any trouble, and none of these are causing trouble here for 0, 1, 1. Here the output needs to be 0, 0. Okay, these two are causing trouble. The output needs to be 1. Okay, so this is causing trouble. The output is 0, so this is causing trouble. This and this is causing trouble. We need the output 1. It is 1, 1, 1 here. This is trouble. This is okay. So that is how we have populated our next table, which is the faults table. And it looks something like this, right? The next step is even more important, where we combine the terminals. For example, ABC and C1, D1. We are clubbing the terms which are showing the same results. If you look at this, you see ABC, they give us same 0, 0, 0, 1, 1, 1. They are the same everywhere. The values of A naught, A stuck at 0, B stuck at 0, C stuck at 0 gives me the same output. And similarly, C stuck at 1, D stuck at 1 give me the same output. So I can club them. And that is what I have done here in this table. Now, the next part is very interesting. In order to check what are the essential input terms, input combinations. The essential input combinations can be found out from checking these columns. A naught, B naught, C naught is causing trouble here for 0, 1, 0. And none of the others, you can see this is not causing trouble, this is not causing trouble, this is not causing trouble, and these two are also not causing trouble. But still, we need to check 0, 1, 0 because it can give me a faulty output when A is stuck at 0, B is stuck at 0, and C is stuck at 0. So 0, 1, 0 becomes my essential input combination that needs to be checked. Alright. Similarly, you can see here in this entire column, only B is present because here in this column A naught, B naught, C naught was present, here B is, and similarly here. Because A stuck at 1 can cause a problem for for 1, 1, 0 input combination, and that needs to be checked because no other condition is there. For example, just look at this case. For example, this case, we are anyway checking 0, 0, 0 input combination because B stuck at 1 needs to be checked, right? And that will also eliminate any problems in C1 and D1. So that will give me an idea what are my essential input combinations. So column wise you need to check where you have just one entry in the column. So in this entire column we have just one entry. In this column we have 3 entries. This is one, these two have 3 entries. So you will be able to make this table of essential test vectors. So is 0, 0 my essential test vector? Yes, of course, because I'll need to check 0, 0, 0 for B1, B stuck at 1, because B stuck at 1 needs to be checked anyway, right? Because it is featuring here in this entire column alone. Similarly, is 110 is an essential test vector? Yes, because A stuck at 1 is causing a problem there, and we are not testing 110 for any other combination of inputs. So this is essential. Similarly, check it for 0, 1, 0, 0, 1, 0. These three could cause a problem, and we are not checking it for any other inputs. This becomes essential. And then what about the non-essential or the selective test vectors? For example, for D stuck at 0, let us see D stuck at 0. We need to check 0, 0, 1, we need to check 1, 0, 1, and we need to check 1, 1, 1, right? So, and for C1 and D1, we need to check 0, 0, 0, and we need to check 0, 0, 0, we need to check 0, 1, 0, 1, and we need to check 1, 1, 1. There should have been crosses here also, or as a matter of fact just one. So out of these three, 0, 0, 0 is already being checked here, 1, 1, 0 is already being checked here. So while checking these essential vectors, C1 and D1 will also be checked, and there is no need to include 1, 0, 0, because 1, 0, 0 needs to check only C1 and D1, and C1 and D1 are already checked by these two vectors. So that 1, 0, 0 is eliminated from our test vectors list. Alright, so that is how you can find redundant test vectors from the combination of essential test vectors and selective test vectors. And I hope this tutorial on fault tables was of help, and if you liked the video, give it a thumbs up, consider subscribing to the channel. I'll see you around. Take care. Bye bye.